Welcome to our complete technical overview of blockchain architecture. I'm going to break down the 4 core layers that make blockchain technology work, walk through how transactions flow through the system, and explain the security mechanisms that make it all possible. Whether you're a developer looking to build on blockchain, or just curious about how this revolutionary technology actually works under the hood, this video will give you a solid foundation. Let's dive in. Main architecture overview. Think of blockchain architecture like a building. It's constructed in layers, with each layer serving a specific purpose. We have 4 main layers. Network layer, the foundation that connects everyone. Data layer, how information is organized and stored. Consensus layer, the agreement mechanism. Application layer, what users actually interact with. Let's start from the bottom and work our way up. Layer 1, network layer. The network layer is the foundation. It's a peer-to-peer network where every participant can communicate directly with others. No central server needed. There are 3 main types of nodes. Full nodes, these are the heavy lifters. They store the complete blockchain history and validate every single transaction. Think of them as the guardians of the network. Light nodes, these are more lightweight. They only store block headers and rely on full nodes when they need to verify transactions. Perfect for mobile wallets and devices with limited storage. Mining nodes. These are the competitors. They're specialized nodes that compete to add new blocks to the chain, and they get rewarded for their work. The network uses a mesh topology, meaning each node connects to multiple other nodes. This creates redundancy and makes the network incredibly resilient to failures. Layer 2, data layer. Now let's look at how data is actually organized. This is where the blockchain gets its name. Each block has 2 main parts. The block header contains metadata. It's like the envelope of a letter. It includes the previous block's hash. This creates the chain, the Merkle root, a summary of all transactions, a timestamp showing when the block was created. The difficulty target for mining, a nonce, the magic number miners are trying to find. The block body contains the actual transactions. This is like the letter inside the envelope. Here's the clever part, Merkle trees. Instead of listing every transaction individually in the header, we use a binary tree structure that creates a single hash representing all transactions. This makes verification incredibly efficient, and SHA-256 hash functions create unique digital fingerprints. Change even one character in a transaction, and you get a completely different hash. This makes tampering virtually impossible to hide. Layer 3, consensus layer, 4 minutes to 5 minutes 45 seconds. This layer is crucial. It's how thousands of independent nodes agree on what's true. Let me explain the 3 main consensus mechanisms. Proof of work. This is what Bitcoin uses. Miners compete to solve computational puzzles. The first one to solve it gets to add the next block and earn rewards. It's energy intensive but incredibly secure, because you'd need to control 51% of the entire network's computing power to attack it. Proof of stake. This is more environmentally friendly. Instead of competing with computing power, validators are chosen based on how many tokens they own and stake in the network. It uses much less energy, but there's a risk of centralization if a few entities accumulate most of the tokens. Delegated proof of stake. This is a hybrid approach. Token holders vote for delegates who do the actual validation. It's faster and more scalable, but even more centralized than regular proof of stake. Each has trade-offs between security, energy efficiency, and decentralization. Layer 4, application layer, 5:45 to 6:30. Finally, we reach what users actually see and interact with: wallet software. These are the interfaces that let you send, receive, and manage your cryptocurrencies or tokens. Smart contracts. These are self-executing contracts with the terms written directly into code. No lawyers needed. The code automatically enforces the agreement. Decentralized applications, or DApps. These are full applications running on blockchain networks, like decentralized exchanges or games. APIs. These provide the programming interfaces that developers use to build all these applications. Transaction lifecycle. Now let's follow a transaction from start to finish. Step 1. Transaction creation. You open your wallet app and send some cryptocurrency to a friend. The wallet creates a transaction that includes who's sending, who's receiving, how much, and your digital signature to prove you authorized it. Step 2. Transaction propagation. Your transaction gets broadcast to the network. Nodes receive it, validate that it's legitimate, and if it checks out, they add it to their memory pool. Think of this as a waiting room for transactions. Step 3. Block creation. Miners or validators select transactions from the memory pool. They organize these transactions using that Merkle tree structure we talked about and create a block header with all the necessary metadata. Step 4. Consensus process. Now comes the competition. In proof of work, miners race to solve the cryptographic puzzle. The winner broadcasts their solution to the network. Step 5. Block addition. Other nodes verify that the winning block is valid. If it checks out, they add it to their copy of the blockchain. Your transaction is now confirmed and permanent. This whole process typically takes 10 minutes for Bitcoin or 15 seconds for Ethereum. Security architecture security is built into every layer. Let me break down the key mechanisms. Cryptographic security uses 3 main tools. Hash functions create unique fingerprints that are virtually impossible to reverse. Digital signatures prove transactions are authorized without revealing private keys. Public-private key pairs enable secure transactions. Network security relies on distributed consensus. Multiple independent parties must agree. Immutability. You can't change history without changing everything that came after. Transparency. Anyone can verify any transaction. Attack resistance includes protection against 51% attacks. You'd need to control most of the network's power. Double spending. The consensus mechanism prevents spending the same money twice. Sybil attacks. Creating fake identities is expensive due to proof of work performance and scalability. Let's talk numbers. Current performance is Bitcoin, about 7 transactions per second. Ethereum, about 15 transactions per second. Compare that to Visa, 65,000 transactions per second. This is the scalability challenge, but there are solutions. Layer 1, solutions improve the base blockchain. Increasing block sizes to fit more transactions. Reducing block times for faster processing. Sharding, splitting the blockchain into parallel chains. Layer 2 solutions work on top of the main blockchain. Lightning Network creates payment channels for instant Bitcoin transactions. State channels enable off-chain computation with on-chain settlement. Sidechains are independent blockchains connected to the main chain. Types of blockchain networks. Not all blockchains are created equal. Public blockchains like Bitcoin and Ethereum are completely open. Anyone can participate, but they're slower and use more energy. Private blockchains are controlled by a single organization. They're faster and more efficient, but require trust in that central authority. Consortium blockchains are controlled by a group of organizations, like a banking consortium. They balance efficiency with some decentralization. Hybrid blockchains combine public and private elements, giving flexibility and access control, but adding complexity. Smart contract deep dive. Let's zoom in on smart contracts since they're so important. The virtual machine layer, like Ethereum's virtual machine, executes smart contract code. It provides a runtime environment and uses a gas system to prevent infinite loops and spam by requiring payment for computation. Smart contracts have several components. State variables store persistent data. Functions contain the executable code. Events provide a logging mechanism. Modifiers control access. Constructors handle initialization. When you interact with a smart contract, a transaction calls a function. The virtual machine executes the code. Changes are applied to the blockchain and results are returned. Integration considerations. If you're thinking about building on blockchain, here are key considerations. For developers, choose the right APIs for your application, plan for wallet integration, optimize for gas costs, inefficient code costs real money. Always get security audits for smart contracts. For enterprises, select the appropriate consensus mechanism, decide between public, private, or consortium networks, ensure compliance with regulations, plan for your expected transaction volumes. And there you have it, the complete blockchain architecture, from the peer-to-peer network foundation, through the data organization and consensus mechanisms, up to the applications users interact with. This architecture enables everything from simple cryptocurrency transfers to complex DeFi protocols and supply chain management systems. Understanding these fundamentals gives you the foundation to dive deeper into any blockchain project. If this helped clarify how blockchain technology works, hit that like button and subscribe for more deep dives into emerging technologies. Drop a comment with what blockchain topic you'd like me to cover next.